Okay, thank you very much. In fact, Stephen Wolfram wrote to me today wanting to explore computational thinking using the language Wolfram. All right, so I'm going to talk to you today about intelligent systems engineering, which is very exciting, and we're making good progress. So by the scale of Purdue, which has over 400 faculty, we're going to be a pretty small program, 30 to 35 faculty in 4 years. And we hope to have around that time 500 undergraduates, 200 masters, and 125 PhD students. This department was motivated by some obvious general principles. No reasonable university doesn't have engineering, so obviously Indiana should have engineering. And also there was a report that pointed out that especially southern Indiana lacked a nearby engineering school because they had to travel up to West Lafayette otherwise. And we also have, of course, extremely strong programs that would both engineering could feed off and would feed into engineering. I noticed it was a non-trip. I mean, our president and others made a wonderful job to get it approved through the Indiana Commission on Higher Education, and that happened on August 13th last year. And that meant that the advertising and things like that were sort of limited. This year we have more time to get out the good word. So this defines you the structure of intelligent systems engineering. It has 6 formal concentrations or tracks: computer engineering, cyber physical systems, environmental engineering, nanoengineering, neuroengineering, and bioengineering. And in the middle you see sort of some of the key building blocks, which are classical engineering, but actually some new things which are not in normal engineering: intelligent systems, big data, modeling and simulation, high performance computing, user interface design, and all the areas associated with robotics and the Internet of Things. All right, so we're a department in the school, and we have this initial group of faculty I mentioned. It has, we'll see it, there are 5 transfers from existing faculty who were in other parts of SOIC. We're located all over the world, unfortunately, but eventually we hope to be located in 2 places: the 4th floor of Luddy Hall and somewhere else, where the only known somewhere else place that is appropriate is called ISAT, which is the old physics cyclotron building, which is a very large building, suitable for the lab space that we need. So currently, as I say, we're everywhere. We do have, most of our people are actually in the Smith Research Center, which is 3 minutes walk away from here. I recommend you visit. We have undergraduates and PhDs, and we're trying to set up activities involving partnerships, which I call the collaboratory. I'll mention that later on. That's with industry and places like Crane. We will have a master's degree, and we will submit that this year, which means that we won't really be able to admit students till fall of 2018. All right. So here are 3 important components which we'll spend time on, not because they're sort of different and not necessarily present in all engineering programs. So the first is intelligent systems. So I normally give the example of, say, a self-driving car. So if you go to Purdue, they'll tell you how to build a car. But if you look at your modern car, it's full of sensors, and it's connected to the cloud and things like that. So it has an intelligent system that people expect in a few years' time will certainly drive that car automatically. So the key part of this engineering program is meant to go from the raw hardware, producing raw data, through decisions and in wisdom and intelligence. So that's what the interpretation of intelligent systems is. Cyber physical systems, well, that's the Internet of Things, and depending on who you read, there are different numbers, but there's 50 to 100 billion things around 2020. And something which we really are keen to have people in is Smart X. If you again read the newspaper, or sorry, the web, you will see about smart homes and smart cities and things like that. So that's meant to be a key part of intelligent systems engineering, and that includes at a lower level embedded systems and streaming data. And the last area I put down here is modeling and simulation. If you look at our initial hires, a lot of them there's an important emphasis on modeling and simulation. And so this engineering program will have in the curricula, both at the undergraduate and graduate level, a significant component on modeling and simulation, which includes high-performance computing, but is not restricted to that. All right. So here's the bachelor's. So there are two existing tracks at the moment. We're approved to do multiple tracks, but we're only doing two computer at the moment, just because we don't have enough faculty to design all of them initially. Those are computer engineering and cyber-physical systems. And this has a core curricula which has 45 credits, and added to that are 6 credits electives and 18 credits which are the different tracks. CE and CPS each are differentiated by 18 credits. Notice this total is 69 credits, which as far as I know is much larger than any other undergraduate degree at Indiana. This allows us to be competitive with other engineering schools. Notice we still have 120 total credits, whereas other engineering programs go above 120, but we wanted to keep to 120. We obviously will aim to do ABET accreditation, but you can't do that until you've graduated your first student. So we have to wait to the bicentennial before we can apply for ABET accreditation. And so if you look at our computer engineering track, I would claim that it's technically as deep as other universities, but it's pretty different. It has, as I pointed out, intelligent systems, modeling and simulation, robotics, Internet of Things, and all that stuff in it. So it's a sort of modern version of computer engineering. And cyber physical systems builds on that and gives you a real specialization in that area, which, well, there's certainly lots of things waiting to have people use them. And we actually just have hired faculty in bioengineering and nanoengineering, and with those faculty, we're starting to design undergraduate programs in those areas. And today we have 25 students who are enrolled in Katie Seeker's teaching E101, the initial course, and next semester there are 2 engineering courses. The PhD. So I should note, though there are 6 formal tracks, there are really 7 tracks, because if you can get a degree without a concentration, and that's effectively intelligent systems. So we are offering degrees in intelligent systems, and we currently have 23 students, and they are distributed over mainly in computer engineering and cyber physical systems, but at least 1 in every one of our concentrations. And I notice, given the interest of Crane people here, we have 2 students from Crane who are working part-time in this program. Here's the faculty. We have 5 senior faculty. Myself, James Glazier, Judy Chu, who's talking out a little later, Tom Sterling, and Martin Swaney, who already talked. And these cover bioengineering, cyber physical systems, intelligent systems, computer engineering, and they give us a very solid base to build on. So we had 100, I point out we had a not terribly well advertised call for faculty, and we had 184 applications for ISE faculty, and I would say they were pretty high quality. We interviewed over 20, and we have 7 faculty joining us this year. 5 have already joined, and 2 are joining in the spring. And they divide into intelligent systems, computer engineering, bioengineering, nanoengineering, and neuroengineering. And here they are. Li Jiang is doing computer engineering, hardware studies. Minji Kim is doing intelligent systems, multimedia, signal processing. Vikram Jadeo is doing nanoengineering, simulations of new materials. Alexander Gumenik comes from MIT and Form Labs, which is a major 3D printer company, and he is building fibers and causing the university great pain because he has very, very stringent laboratory constraints, which we are challenging the university to meet. I'm not certain they will meet the challenge. We will see. Well, I can't pronounce Eleftherius' name, but he's in the audience and can tell you how to do it. And he has a wonderful software lab, open source imaging for MRI, which is a wonderful collaboration with PBS, Psychology and Brain Science in COAS. And he has a PhD in cognition and brain sciences from a pretty reasonable university, Cambridge. Maria is in bioengineering. She works with zebrafish and is particularly expert on toxicity, which is a pretty interesting area which we're writing in the AR in, or she is writing in, and others are writing in the AR in. And she's from Houston. And we have an acceptance from somebody who doesn't want his name revealed, who is doing cancer modeling and data analysis. So a couple more slides in the 2 minutes. So we have to make 50 courses in 4 years. Because remember, we had 23 courses required in the engineering undergraduate, and we better give them a little bit of choice. And of course, we have some graduate choices. That ends up back about 50. And yet, all the faculty are required to submit NSF career awards and hopefully succeed. And so they need to be research very active because we want to be a top-notch engineering school. So that's not so easy to see how to do. So we will be using lecturers to help us prepare these courses, where hopefully the faculty will spend more time designing courses and not so much time delivering them. And we will use online technology to do that, so that we can design and create the courses independently of the delivery. This would mean we probably will be able to offer at least some majority of the courses online and potentially offer online degrees. And there was somebody from Crane who wrote to me saying he wanted a master's in computer engineering online. So we might be able to do that. And the last slide just says that we need to have a strong partnership. Actually, ABET requires that. We need an industry advisory board. And back in the past, Bill Wolf from Virginia proposed the collaboratory, which is sometimes called in the virtual organization. And so I see that as a useful way of implementing a set of partnerships across the campus, across the region, and across the world. And so we want to therefore have sort of ISE faculty and a very strong collaboratory which we organize and offer benefits through, and including an industry consortium, some NSF funding through the IUCRC program. And say the collaboratory will end up obviously significantly bigger than the department. And we're just starting to set that up. So that's intelligent systems engineering. I'm happy to answer questions now or later, whenever there's time. Thank you.